So far we have done forces, and we have launched things up in the air. They've fallen down to the ground. We've launched things at an angle, off the top of things. We've pushed, we pulled, we've moved things uphill, we've done friction. It's all been very exciting. Now we get a turn. Now we've built enough that we can actually start turning our cars instead of driving in straight lines, which would be really boring. You'd be like NASCAR and go in circles forever, which would also be equally as boring, but that's okay. And I'm told that I have this car, so I guess you'd think of the car as going this way instead of this way, but it's my world, so this car is going that way. Going to be making a bunch of right-hand turns. So let's remind ourselves of a couple of things. First of all, I said that in order to change motion, in order to change it, to change motion, I need a net force. And I reminded you, as we've been doing these things, that a net force, well, that's required for change of motion in the magnitude of a velocity. So either change, let me do a different color because this is important, either change the magnitude of the velocity, and those little lines right there mean magnitude, or direction. So if I get something, I need a car or something. If I get something going in a straight line, if there's no forces acting on it, once I give it a shove, it would keep going in a straight line. This is pivoting. Oh, stuff we're going to talk about this week, but hold on to that. This one's pivoting just because of the way its mass is distributed. So I don't have a frictionless surface. This thing won't continue moving. But if I did have a frictionless surface, that perfect surface we talk about all the time, once I gave it the shove, I could take my hand off and it would keep going. Think space. Think space. When something gets going, it will keep going until something acts on it to change its velocity or its direction. In space, this is often gravity. So you could think in terms of a satellite orbiting. It doesn't have any fuel. The force due to gravity is the thing making it go in a circle. So we have to have a force. And the way we define how something is accelerating, or what the direction of the acceleration and the net force would be, is we say the net force, let me move the car up here so it's going to be more of a straight line. The net force points towards the center of the circle. And so even if I'm going on a corner, I don't know, out on the road anywhere, a freeway off-ramp, or whatever the case may be, it doesn't need to be a complete circle, but I can take any arc and complete it into a circle, even when it's that badly drawn. So my force net is pointing towards the center of the circle, towards the center of the circle. And my acceleration is also pointing towards the center of the circle. Now, you'll see these things kind of labeled different ways, and one of the ways that you'll see the force net labeled is like force center. And acceleration, depending on who's writing it, it's either going to be like a center-seeking acceleration or radial acceleration. You can see it written either of those two ways, and for our purposes, they both mean the exact same thing. Force center, though, this is the one where everybody gets all kind of crazy, and we get excited, and we say, well, that is a fictitious force. Fictitious, yeah, I won't write it all out. That's a fictitious force. And all we mean is that this C stands for any number of forces. In the car example, that would be friction. If I tie something to a string and swing it, the thing making it go in the circle would be the string. So that would be the force of tension. So they're both center-seeking forces. They're both causing something to turn. but they're not the same force, and that's what's important to keep in mind. So my fictitious force, what we're saying is that Fc is not one single force. It can be anything, one single force. It's whatever force is allowing you to go in that circle. And this is one part that people start getting hung up on when we're in class. And I said, what's making you go in the circle? And most students will say, my tires. Well, okay, that's valid. That is valid. But it's the tires in contact with the road that make that circular motion possible. So think about it, if you've ever driven on a snowy day and you're trying to go around a corner, like get on the freeway or whatnot, and as you go here, if you hit ice, you're starting to turn, what you're going to keep going because you need that friction for your tires to hold on to make that turn. So it's the force of friction between the tires and the road that makes that turning motion possible. For the tension on a line, yeah, the thing is connected and I have tension, I'm sorry, I would have like a connecting point here, but it's actually the tension on the line that would make, say, a ball attached to the end of the line swing, or a pendulum. There's all sorts of things we can do there. And so we have this. Let me define one more thing before I go and we do some fun math with this, is that this center-seeking acceleration is defined in terms of v squared over r, where r is the radius. This is the radius of the turn. Radius, I can't spell today. It's the radius of the turn. And you'll either be given generally the radius itself or something in terms of diameter. So one thing you want to remind yourself is that diameter equals twice the radius. Diameter, yeah, spelling has left me, equals 2 times the radius. So if I'm given the diameter of a circle, right, that would be, the diameter would be from one side of the circle to the other. If I cut that in half, then I have the radius, because the radius is just defined as 1 point to the center of the circle. So you just divide it by 2. The other big thing everybody gets hung up on is when we do small things, these values tend to be in terms of centimeters. That in our world, everything needs to be in meters, kilograms, and seconds. So you'll be given things for your distances in terms of centimeters, and oftentimes this will be in terms of minutes, or if we're doing satellites, days or hours. But to do any math with it, I have to have it in these units. See what else is there. So we know that there's a force that's required to make this turn. So let me write this out then, because we already know if I have a net force, force net equals MA. So if I have a net force, a net center-seeking force, that's going to equal, here's my A, there's my center-seeking acceleration, V squared over R. I want to emphasize, though, that this doesn't have to be just one thing, and oftentimes it tends to be more than one thing. So this is going to be whatever net piece points towards the center. So I can have more than one force contributing to this. We're going to do the exact same thing where we're going to do a summation of forces and figure out what piece is making it go into the center, and that thing will give us the center-seeking acceleration, or this center-seeking acceleration here. That V, well, heck, that is our tangential velocity. All around this corner, my velocity goes like this. And for now, if I draw on a prettier picture, these would be all my V's, my V tangential. For now, we're just going to be happy considering that this velocity is constant. So that's kind of the fun part, is now I've gotten you used to seeing that constant velocity means no net force. Well, now I can have constant velocity. If I'm turning, I have to have a net force, and it has to point towards the center of my circle. So with that, I think we're ready to have some fun.